And welcome friends. In this particular module, I am going to discuss about the determination of the latitudes, departures and determination of the accuracy in Theodolite traversing. Briefly, we will get introduced with the concept. We will deal with the angle misclosure in traversing. We will understand the balancing of the angles, computation of the bearings, latitudes and departures. We will also discuss about the error of closure and applying checks on open and closed traverse. So as you learn the content, you will be able to determine the angle misclosure, check the misclosure with its permissible limit, and if it is lying within the permissible limit, adjust the same by making use of arbitrary, average and rounded off methods. You will also be able to compute the bearings, and by making use of that reduced bearings, you will be able to determine dependent as well as independent coordinates for that particular traverse. You will be able to apply the checks in open and closed traverse and also to work out magnitude and direction of closing error. Let's try to understand some concepts about this particular permissible angle of misclosure. If we are dealing with certain closed traverse, then theoretical sum of all the included angles should be equal to 2n minus 4, 90 degrees. If the traverse is run by deflection angles and if the links, that is the sides of the traverse, are not crossing each other, the algebraic sum of all the deflection angles should be equal to 360 degrees. Here, angles towards right we treat as positive, whereas angles towards left we treat as negative. If the traverse is run by bearings, initially measured bearing of the first traverse link should be same if it is remeasured as we follow all the links of traverse and as we come back to the original station at the end of the work. So here the misclosure is the difference between the actual sum that we compute and the theoretical sum that is worked out for the kind of the traverses that we discussed above. Usually for Theodolite traverse, this permissible angle of misclosure is given by expression E is equal to K root M. For ordinary Theodolite, the least count is 22nd. Here it is treated as value of K and M is number of traverse link. So if the traverse has 9 sides, the permissible angle of misclosure would be 60 seconds, that is 1 minute. It is needless to say, if the angle misclosure is observed more than its permissible value, the entire work needs to be repeated, whereas if the angle is remaining within the permissible limit, it can be appropriately adjusted as we discuss further. So, this appropriate adjustment is termed as balancing of angle of misclosure. We have various methods for that. The first method is treated as arbitrary. So here the actually observed error is considered and with its opposite sign is applied at a particular station or at the stations which are suspected to be erroneously measured. So this method is arbitrary. It is the sole understanding of the surveyor, and accordingly he applies the correction. Second method is very common, which is termed as applying the outage. So here, as given in this particular example, as you see, here the actual sum of all included angles as measured on the field works out to be 539 degrees 59 minutes 40 seconds. Whereas, as the traverse is 5-sided, the sum should be 540 degrees. That is, misclosure works out to be 20 seconds. Giving consideration to our permissible error concept, the permissible closure could be plus or minus 44.72 seconds for that 5-sided traverse. Here, as the error is within the limits, now it can be just averaged out as 20 seconds by 5, that is 4 seconds. The sum observed is less than the theoretical sum. Hence, the correction of plus 4 seconds is applied in each of the angles measured at each of the stations. Now, as you see here, the last column, that is adjusted angle, the last figure gives us 28 second, 24 second, 44 second as such. So, if there is some other person who is referring to these particular adjusted angles, he will have certain wrong impression that all the angles are measured with 1 second theodolite, which is not practically the case, because as we know, theodolite has got least count of 20 seconds. So this is one of the lacunae for this particular method. In order to avoid that, we can go for this rounded off average correction. So, say for traverse with 5 sides, the misclosure is of 1 minute. Hence, by assuming this particular misclosure, we can apply this particular correction in the multiple of the average correction in this particular column. So, the way you see minus 12 second, minus 24 second, minus 30 second, and accordingly. Now, here this particular value will be rounded off to its nearest 20 second in next column. So here this particular 24 second will be considered to be 20 second, 30 second could be considered to be 40 second, 48 second could be considered to be 40 second. Here that particular 60 second would be considered as 60 second, whereas initial value is considered to be 0. So in this particular third column now, we determine the successive differences by subtracting the preceding value in the column C2 from the one being considered. So here, as we get these particular C3 values as 0, here 20 second minus 0, it will give 20 second. 40 second minus this particular preceding value 20 second, it will give you minus 20 second. 60 minus here, that particular 40 minus 40 will give 0. 60 minus 40 will give again minus 20 second. So all such values that are averaged out would be considered as correction to correct this particular observed value. As such, here angle A is 101 degree 14 minute 20 second. It is remaining as it is because C3 has value 0. Here the angle B is 230 degrees 54 minute 20 second. As we apply the correction of minus 20 second, the corrected angle, adjusted angle will be 230 degrees 54 minute. As such, we can have all these particular corrections rounded off in order to avoid that wrong impression of measuring this particular angle with 1 second theodolite. Another consideration before going to theodolite traverse computations is nothing but the computation of the bearings. In earlier discussions, already we have discussed about the compass traverse, and you know how the bearings can be used in order to compute the subsequent bearings. So for a given figure, the bearings are to be computed from a line of which the bearing is known by using corrected angles, and as discussed previously, the bearing of the line measured in forward direction of the survey line is nothing but the fore bearing. It can be determined by back bearing plus or minus 180 degrees. In the similar manner, the back bearing is nothing but the back bearing of line measured in the direction opposite to survey line. Now, having the corrected bearings as well as the corrected angles for a theodolite traverse, we can compute the latitudes and departures. As you see here in this particular figure, we are considering certain line AB, which is nothing but the side of certain theodolite traverse. It is making inclination of the theta with respect to this particular magnetic north. Hence, this theta can be considered as reduced bearing. So, having known these particular values of this particular reduced bearing and length of that particular side, now we can have the projection of that particular line on north-south axis as well as east-west axis. So, the latitude of the line is the component of that particular major distance parallel to north-south direction. Here, as you see, for line AB, latitude is expressed as capital L with a value L cos of theta. In the similar manner, departure of this particular line is the distance measured parallel to this particular east-west direction. So, for line AB having length L and inclination of theta with respect to magnetic north, departure will have the value of L sin theta. As we consider the various quadrant, So in the first quadrant, both latitude and departure will be positive. In the second quadrant, latitude will be negative, whereas departure is positive. In the third quadrant, latitude will be negative, as well as departure will also be negative. Whereas in fourth quadrant, latitude will be positive and departure will be negative. Conventionally, in order to have the computations, latitude towards north is termed as northing and it is treated to be positive. Whereas, as you see here in this particular sketch for a certain line OB, latitude towards south is considered as southing and its value is considered to be negative. Similarly here, say for line OA, departure towards east is considered to be easting with positive value, whereas for line OE as well as line OC, the projection on the west is treated as westing and it is termed with negative sign. If we work out this particular, say, latitude and departure, we can follow the other terminology which is called as dependent and independent coordinates. So, for a given traverse, the coordinates of the endpoints of a line with respect to the initial point are called as consecutive or dependent coordinates. So, in this particular figure, the coordinates of this particular station B of a line AB with respect to station A are minus L and plus T. Here, as you see, these dependent coordinates are nothing but latitude and departure with their proper sign, as we discussed in the previous slide. Whereas, if we work out the coordinates of any station with respect to the common origin, they are called as independent coordinates or the total latitude and total departures or total coordinates. So here, as you see, the entire traverse is made lying in the first quadrant. As such, both all that particular latitude as well as departure will always be having the positive values. Hence, just for sake of understanding, as you see here for station B, with respect to this particular common origin, the coordinates are XB and YB. Similarly, for station A, the total coordinates, as you see, are XA and YA. As such, in order to determine the total coordinate at any station, here we have to start with the initial station. So, total coordinate of this particular starting station plus the coordinate of station B with the proper sign plus coordinate of this particular line up to station C. As such, the total coordinate of any station is expressed as total coordinate of this particular starting station plus the algebraic sum of all the coordinates of the stations up to that station under consideration. Already you know about the closed traverse. So here, as you see, this particular traverse AB, BC, CD, D, E, it is started from station A and it is closing again on station A. As such, it is treated as closed traverse. Other terminology that we discussed about this particular traverse is nothing but the link traverse. That is, we start from, say, some known station B. We follow various survey lines as B, E, C, CD. Here again, this particular station D is known, its coordinates are known. As such, this is treated as link traverse. So for this particular closed traverse, as you see here, for line AB, the lengths can be known, their reduced bearings are known, and the consecutive coordinates, as we discussed earlier, can be expressed as northing, southing, easting, westing in respective columns. Otherwise, as you see here, for respective lines, giving consideration to these particular reduced bearings, the latitudes and departure can be expressed as their appropriate sign. So, for this particular closed traverse, the sum of the northings should be equal to sum of southings, as well as sum of eastings should be equal to sum of westings. Just in other language, here the algebraic sum of latitudes must be equal to 0, as well as algebraic sum of departures must also be equal to 0. In open traverses, where the starting station and ending station is different one, direct checks for angular measurements are not possible. Hence, some indirect checks can be made. Here, as you see in figure AB, we have considered certain line AD, DG as cutoff line. So, theoretically, A, B, C, D, A is nothing but a closed traverse. Similarly, here D, E, F, G, D is also the closed traverse. So, by having some such, say, cutoff line, we can assess the plotted length and its direction, and we can apply the check in the open traverse. Similarly, here, say, we can define certain auxiliary station P. We can measure the length and bearing of this particular station with respect to certain selected stations. As we plot all the direction and lengths in order to define the location P, here the position that we got from that particular respective station should be reasonably at acceptable level. In addition, say if we are working on some such traverse AB, BC, CD, we can tie this open traverse with certain known tie station. So here, say it could be triangulation station. So having that particular triangular station, we know their coordinates. So as we work out the coordinates for that station, theoretically and the one which are practically observed should go hand in hand. Otherwise, we can also have some, say, separate traverse to close this particular open traverse, and as if it is, say, closed traverse, we can apply the check. If the network is very important, say for example, if we are working with certain geodetic survey or such, usually we refer to some stations and we have astronomical observations to determine the true bearings, and as we compare these particular true bearings determined from these astronomical observations can be compared with the calculated true bearings, and accordingly we can apply the check on open traverse. If for closed traverse, if the criteria is not satisfied, the traverse will not be closed as we plot. Here, the criteria is nothing but the algebraic sum of latitude should be equal to 0, as well algebraic sum of the departure should be equal to 0. Usually, the angles for Theodolite traverse are measured with better accuracy as well as they are corrected one. Hence, this error of closure is mostly due to the erroneous linear measurements. So, as we discussed previously, if the error of closure is within acceptable limits, the traverse can be adjusted. Here, as you see, we started from this particular station A, we followed the links BC, CD, DA. That means we have closed the work practically on station A, but as we plot this particular traverse, here as you see, the station which is plotted for A is not A but A dash. As such, here it has closing error AA dash. It can be considered again its two respective components as EX and EY, and hence this can be considered as error triangle. With their opposite signs, we can have the correction triangle. So, as we consider this particular, say, EX, EY, we will be able to compute the sum. Here, for a closed traverse, that EX should be nothing but that summation of the departures, as well as this EY should be nothing but the summation of the latitudes. So here, as you know, we have this particular algebraic sum of latitudes and departures. It should be 0 for the closed traverse, but if there is some difference, that means well beforehand, well before plotting, we will be able to know that the traverse is not getting closed, but it has got certain error E, and their components are EX, which is nothing but the algebraic sum of departures, as well as EY, which is nothing but the algebraic sum of latitudes. In the similar way, the way we discuss about the link traverse, we start from known station, we close the work from known station. Hence, say if x and y are known coordinates, and for link traverse, if the x dash and y dash are computed coordinates, the difference in the known coordinates and computed coordinates will be their respective error components. Here, this error E can be worked out as square root of EX square plus E square Y. Also, its direction will be given by tan theta EX by EY. As such, as we work out the inverse of that theta, we'll be able to know in what quadrant that particular line is like. Also, for closed traverse, the relative error of the closure is expressed as error of closure divided by perimeter of the traverse. While discussing about the errors in surveying, we have given consideration to this concept of relative error in depth. Usually, this relative error of the closure is expressed as 1 by P by E, and it is also called as relative accuracy or degree of accuracy. In our earlier presentations, we also got acquainted with the compatibility of the measurements. So, we know that for any traverse, we have to have the methods chosen such that linear methods would be compatible with the selected angle measurement methods and vice versa. So, for a traverse based on the compatibility of the measurement, for expected precision of 1 in 5000, the allowable angular error could be 41 seconds. Whereas, for expected precision in angular measurement, the allowable linear error could be 1 in 10,000. So, as angles are balanced initially, errors in linear measurement would be major factor. Here, as a guide value, the order of accuracy, that is the permissible degree of accuracy, can be considered for the kind of the traverses that we are dealing with. So as you know, we have discussed this concept also earlier, that if the traverse is of first order, the accuracy will be highest one, whereas as compared to that particular, say, first order traverse, the fourth order traverse would be much inferior. Hence, the relative accuracy in linear measurement can be considered to be 1 in 25,000, 1 in 10,000, 1 in 5,000 and 1 in 2,000 for the traverses of first order, second order, third order and fourth order respectively. For the order of traverses, we can work out the relative accuracy in angular measurements by making use of these particular respective expressions. So here, these particular values will assist us to determine the relative error of closure. So, I thank you very much, students. Thanks for your attention. As we move ahead, we'll discuss about traverse computations and balancing of the traverse by making use of various methods. So bye till then, I wish you very happy learning. Thank you.